Hi everybody, and today we will start a new topic. I want to discuss magnetic field and magnetic properties of direct electric current. Magnetic phenomena have been known to people since many thousands years ago, because people found pieces of iron ore, just iron ore, on the surface, like stones were found on the surface of the planet Earth. And these pieces of iron ore possessed magnetic properties. They were interacting with each other. Two pieces interacted with each other. And they could be attracted to one another, and they could be repelled if you turn it by 180 degrees. Then there will be repulsion, a repulsion of two pieces of magnetic substance. So either attraction or repulsion, depending on how you turn these stones with respect to one another. And this was always an interesting phenomenon. And more than 2,000 years ago, a compass was invented in China based on the properties of magnetic materials. So if you take a small elongated rod made of magnetic material and suspend it on a thread like that, then this small rod will be freely oscillating, and after the oscillations have decayed and ceased, this small rod will show the direction from north to south. And this phenomenon was discovered in China more than 2,000 years ago. And based on this phenomenon, they invented a compass, a simple device which allows one to navigate in the open sea. Magnetism is a very long known phenomenon, but the study of magnetism, the scientific study, began practically 200 years ago. Just a little bit more than 200 years ago, in the beginning of the 19th century. First of all, there is a simple way to visualize the magnetic field. What do we call a magnetic field? If you take a piece of magnet, like a bar magnet, which has two magnetic poles, one is the North Pole and another is the South Pole, then this bar magnet will interact with similar magnet, either through attraction or through repulsion. And this interaction takes place through an empty space. But even in the vacuum, as we now know very well that magnetic interaction takes place even in vacuum. But how can anything propagate through vacuum? It means that vacuum is not merely an empty space. There is something. There is something which conveys the magnetic interaction, as well as electrostatic interaction, as well as gravitational interaction. So vacuum is a complicated medium which possesses a lot of complicated properties. And so the magnetic field is some distortion of vacuum, some change of vacuum properties. And this area, this volume of vacuum, of space where the magnetic field can be discovered, this volume is called a magnetic field. The magnetic field is something which happens in a vacuum, in the vicinity of a magnetic material. So the magnetic field can be visualized, and unfortunately the physical classroom is now closed, and I can't show you physical demonstrational experiments, but imagine a piece of glass with which we cover this bar magnet. So there is a piece of glass which just covers the bar magnet and lays over it in such a way. And if we spread some iron powder on the glass, the iron powder will be just distributed here randomly. And then if we tap on the glass, just to shake it a little bit, then the iron powder will arrange in such a lines. The iron powder will show the structure of magnetic field. And it will be visualized in such a way that you will see such a lot of many such curves, starting on the one pole and ending somewhere on the other pole of the magnet bar. And if you look at such a line through a microscope, for example, you will see that small pieces of iron powder just link together to form such a line, which is a visible magnetic field line. Like that. So, for example, if we look through a microscope at this place of a magnetic field line, we will see that the grains of iron powder are arranged in such a way. Well, now we know very well that each grain of iron powder gets magnetized in the external magnetic field in such a way that one end of this grain will act like a north pole of small magnet, and another end will be a south pole. Just like here, we have a north pole and a south pole, and each grain will have a north and a south pole. Each grain will become a small magnet, and so that unlike poles will be attracted to one another, and in this way all the grains of iron powder will be aligned along such a line of field here if we look at it through a magnifying glass or through a microscope. Well, as the piece of iron can be magnetized in an external magnetic field, people said that the magnetic properties of this piece of iron have been induced by the external magnetic field, and therefore such field lines have been named an induction lines, and the magnetic field is characterized by some induction. Induction is a vector. In each point of space, this is a vector because this physical quantity which has a magnitude and a direction. The magnitude of induction is larger if you go closer to the magnet pole, and it becomes smaller if you go farther from the magnet pole. So this induction has varying magnitude in space and varying direction. Here is the direction. In this point, the direction of this vector is such that it looks in this way, and here it will look in it will have a different direction. But anyway, the direction of an induction is assumed to be from the north pole to the south pole. So every magnetic field line has a direction which is starting or flowing from the north pole and goes to the south pole. And the induction lines can be visualized using the iron powder on a piece of glass. And the name induction originates from the fact that each piece of iron has an induced magnetic properties. If you take separately a piece of iron, just a piece of iron, it may have no magnetic properties. It may have no macroscopic magnetic properties. But if you put this piece of iron into the magnetic field here, then it will be magnetized and it will have its own north and south poles. And so the magnetic properties will be induced, and therefore the magnetic field vector is called the induction vector. Induction of the magnetic field. So in the year of 1820, a very interesting experiment was carried out with magnetic fields. And the experiment was carried out by Ørsted in Copenhagen. So the experiment was this. He took a straight wire with a direct electrical current, and he discovered that such an electric current creates a magnetic field around it. And the magnetic field lines, the induction lines, can be easily observed in this case just in the same way by using the iron powder. And the magnetic field lines all are circles lying in a plane perpendicular to the current, so that the magnetic field lines can be depicted in this way. All of them are circles, circular lines. So the magnetic field vector here will be directed in this way. That is the discovery of Ørsted, which was made, well, 201 years ago. The direction of the magnetic field can be found using the so-called right-hand rule. If you take a right hand and put it in such a way that your thumb will show the direction of the electric current, then your fingers will show the direction of the circular magnetic lines surrounding this straight wire with electric current. So such will be the direction of the magnetic field. Well, this discovery made it possible to create artificial magnetic fields, because before this discovery, the magnetic fields could only be obtained using the magnets, the natural magnets found in nature, just like pieces of iron ore. And the natural magnet is good, it's constant, it produces constant magnetic field of constant configuration. Anyway, the properties of such a bar magnet are complicated, because, for example, if you heat this piece of bar magnet to some temperature, then the magnetic properties will vanish. They will disappear, and the magnetic field will disappear. So not everything is so simple with bar magnets. But when people, due to Ørsted, found it possible to create artificial magnetic fields, then it became possible to create magnetic fields independently of any constant bar magnets. And the magnetic field could be varied. We can change the intensity of the induction of magnetic field if we change the strength of electric current. The larger the electric current, the larger will be the magnetic field created by it. So experimentally, it was found experimentally that the magnetic field strength turned out to depend on the distance of the point of observation, distance r, of the point of observation from the wire. And the magnetic field strength turned out to be proportional to the strength of electric current and inversely proportional to the distance from the electric current. In the same year of 1820, a French physicist, Ampere, made another discovery. He discovered that two straight electric currents, that is, two straight wires carrying the electric current, interact magnetically with each other. they interact magnetically. So that the two like currents will attract to one another with some force F. And if you take two unlike currents which flow in different directions, then they will be repulsed from one another. And these forces of attraction and repulsion between the straight electric currents were called Ampere Forces. Ampere Forces, forces of interaction between the electric currents. So the logic of this discovery was as follows. Each electric current creates a magnetic field in the space around it. So this electric current creates a magnetic field around it. And this magnetic field created by the first electric current is interacting with the second electric current. And for this reason, the second electric current is acted on by some force from the magnetic field created by the first electric current. So this is magnetic field B1. In the same way, the second electric current creates a magnetic field around it of the same structure. And this magnetic field created by the second current will interact with the first current and act with some force on the first wire, on this wire, with the current. So that these two forces, the force acting on the second wire and the force acting on the first wire, must be equal in magnitude and oppositely directed due to the Newton's third law. Well, as the current creates a magnetic field, Ampere was aware of these experiments and of this result. He understood one important thing. He understood that if we take not a straight wire, but a wire which makes a loop. So we take a wire which takes a loop, makes a loop, so that the electric current flows here in this wire loop and then goes out through this wire. The electric current enters through the wire and then goes around the loop and exits this loop. So in this way, the electric current, each small element of electric current will create its own magnetic field, and the space structure of this magnetic field will be shown by this picture. So that if we have an electric current flowing in this direction, then the magnetic field will form such circles. And here the magnetic field of this current will form similar circles. But the magnetic field of this electric current will be directed inside, will be directed in such a way that it will be directed from this wall to the audience in this way. And the electric current on the opposite side of the wire will be directed in the same way to you, from this wall to you. And so all the magnetic fields inside this loop will be directed in such a way that they will show here. And the outside of the loop, the magnetic fields will be directed oppositely, that is, from you to the wall. If we look at this current loop of current from the side, if we take a side loop from here, then we will discover that the magnetic field inside goes in one direction and the magnetic field outside goes in another direction, so that the magnetic field lines are arranged in such a way oh no, in such a way that this goes here, and this, yes, that's it. So we look at this current loop. We look at from here, from that is our eye, that is a human eye. I look at it from the side, and the side look from this side. This loop will look like just a flat wire. So the loop is here, the loop is current, and the magnetic field will have such a structure. Comparing this magnetic field with the magnetic field of a bar magnet shows that there is some similarity. It looks like we put here a bar magnet vertically, and the bar magnet field will have the same structure. It will have the same structure as the field of a current loop. Well, analyzing this situation, Ampere came to such a conclusion that the bar magnet creates a magnetic field because there are some internal electric currents in it. And Ampere assumed that an electric current flows inside each molecule of the bar magnet. And each molecule will have an electric current flowing around it. So there are molecules of the bar magnet, and the electric current flows in the same direction, like counterclockwise. And so on. There are many, many molecules. But look here, inside the bar magnet, there is one electric current flowing in one direction and another electric current flowing in another direction. So these two currents will cancel each other. Also here, this current flows upward and this current goes downward. So these two currents cancel each other. So there are actually no currents inside the magnetic bar. But on the surface of the magnetic bar, on the surface of this magnet, there is some current flowing on the surface, some electric current flowing like on the surface due to these molecular currents. Such was the picture of magnetism assumed by Ampere, and it turned out to be correct. All the present-day investigations confirm such picture. It turns out to be correct. Magnetic properties of magnetic materials, like a bar magnet, are due to molecular currents which flow inside each molecule. And these currents are compensated or cancelled inside the bar material, and only the current flowing on the surface of the bar creates the magnetic field. But this current on the surface looks like a current loop. Like here, we considered a current loop. So all the magnetic bar consists of some current loops, and therefore the structure of magnetic field created by the magnetic bar is the same, looks like this, the same structure which is of magnetic field which is created by a current loop. But in this case, the current flows on the surface of this magnetic bar. Now, if we create a loop of wire and we allow a direct current, electric current, to go in this loop of wire, then this circular electric current will create magnetic field in the space. It will have some magnetic properties by itself. But what will happen if we insert this loop of wire into an external magnetic field? So here is an external magnetic field, and I will show the field lines. That is an external magnetic field. And I will consider a uniform magnetic field with uniformly distributed magnetic lines. So in every point of space, the magnetic field is the same. What happens in this case? Well, if we look here into the interaction of magnetic field with a current, we will understand that the magnetic field line in this point is perpendicular to the current, because magnetic field induction vector is directed to the wall and the electric current flows upward, and the force of interaction is directed here. So the force of interaction is perpendicular both to the current and to the magnetic field vector. The force of interaction is perpendicular both to the current direction and to the direction of magnetic field induction. So, if we arrange such an experiment, then the same will be here. The same phenomenon must be observed here. The electric current goes upward and the magnetic field induction is in this direction. Therefore, the force of interaction between this current and this magnetic field must be perpendicular to both the magnetic field and the current. So in this case, the magnetic field the force of interaction must be directed, must have one direction, and here the direction of magnetic field is the same, but the direction of current is opposite in these two opposite legs, on the opposite sides of this loop. So the force of interaction between the current and the magnetic field here must be opposite, so that these two forces will tend to turn this loop of wire, because the forces will have different directions. And such two forces attempting to turn any object are called a pair of forces, and the pair of forces are described by a torque. A torque, I will remind you, a torque, if we denoted it by M, will be equal to the force times the arm of the force. And the force is the force acting on one side of the loop, and the arm of the force is just the distance from the force where it's applied to the axis of rotation. If this loop of current may rotate about this axis, vertical axis, then there will be a torque acting on this loop. And it turns out that the torque acting on the loop is proportional to the magnetic field induction and the strength of the electric current, and also it's proportional to the area of this loop. So this is the area of the loop, which is measured in meters squared or centimeters squared. So there is some area S of this loop. And the larger the area, the larger will be the torque acting on this loop. This is an experimental fact. This is an experimental fact that there will be a torque tending to rotate this current loop, and the torque is proportional to the magnetic field's induction vectors and the strength of the current and the area of the loop. The larger the area, the larger will be the torque. So this is an experimental fact. And this experimental fact allows one to measure the magnetic field induction vector, which is here, because all the other physical quantities which are involved in this equation can easily be measured. We can measure forces, and we can measure distances. So we can measure the torque acting on the wire loop, and we can measure electric current. We know what is the current strength, and certainly we can measure the area, because we make this loop by ourselves. We know what is the area of this loop. Therefore, this equation allows one to measure the magnetic field induction, which will be equal to the torque and will be divided by the current, electric current strength, and the area of the loop. This quantity, electric current times area, is called the magnetic moment of the electric current loop. That is the magnetic moment. Therefore, this formula can be written as the torque divided by the magnetic moment. the larger the torque, the larger is the magnetic field induction. What will be the units of measurement? I will show only the units of measurement. The torque is measured in newtons, which is the unit for force. And then the arm of the force is just the distance measured in meters. And the electric current is measured in amperes in the international system. And the area is just measured in meters squared. So the units will be Newton divided by ampere and meter. And such a unit is called Tesla. This is Tesla, capital T. This is Tesla, capital T. 1 Tesla turned out to be very strong magnetic field, very large magnetic field. I should say that the magnetic field created by our planet Earth, our planet has its own magnetic field, is about 10,000 times smaller than 1 Tesla. So the magnetic field of our planet is about the magnetic field of Earth. The magnetic field of our planet Earth is about of the order of magnitude 10 to the minus 4 power. That is 10,000 smaller than 1 Tesla. That is the magnetic field of our planet. The magnetic field of our Earth is non-uniform field. It is stronger closer, if you go closer to the pole, to the North Pole and to the South Pole, then the magnetic field of the Earth will be stronger. And it's the smallest near the equator of our planet. And also, if you go farther from our planet into the outer space, that will be smaller and smaller. The magnetic field will fade away. But anyway, by the order of magnitude, it's about 10,000 times smaller than 1 Tesla. And so 1 Tesla is a strong magnetic field. It's in order to create a field of 1 Tesla, you need large equipment, heavy coils in the laboratory in order to make such a field.
But the question of the induction.
Yes.
Yes, it says it's direct proportional to the torque.
Yes.
Yes, but it is inversely proportional to the current. So the current is downward.
Yes.
No.
B is inversely proportional to current. Yes, if we find B from this equation, we will find it as M divided by IS. That's correct. And IS is the magnetic moment of the current loop. That's correct. Yes, exactly so. The larger the current, the larger will be the torque. So these two quantities are proportional to one another. And if the current is 0, then the torque is 0. So nothing happens here especially interesting. These two units are proportional to one another. Two quantities are proportional to one another. So such is the way to measure, actually, this is the way to measure the magnetic field induction. This is a real method of experimental measurement of induction. People take a small loop of current, but in experiments, this loop of current is made of many turns of thin wire. So there may be hundreds and thousands turns here, hundreds of turns, so that the magnetic moment, the area will be larger and larger. The larger the area, the larger will be the torque, and therefore such a device will measure smaller magnetic fields. So people take many turns of wire, and therefore the area will be large, and therefore it will allow one to measure small magnetic fields, as small as millions of part of a Tesla. But there are other physical phenomena which allow one to measure very small magnetic fields. There are some interesting phenomena which are called nuclear magnetic resonance. Devices or magnetometers based on nuclear magnetic resonance allow one to measure very small magnetic field, like many thousands times smaller than a nanotesla. A nanotesla, 1 nanotesla is 10 to the 9th power of Tesla. So it's 100,000 times smaller than the magnetic field of the Earth, 100,000 times smaller. But the modern magnetometers can measure magnetic fields even millions times smaller than this one. That's based on nuclear magnetic resonance phenomena. So if you need to measure very small magnetic fields, like interplanetary magnetic fields in outer space, which are very small, then you need to use such a device based on nuclear magnetic resonance. But if you need to measure relatively large relatively strong magnetic fields, then there are other devices based on such a electric current loop and the torque acting in such in a magnetic field on such a loop. So there are many different devices known to modern engineers how to measure, which allow to measure the magnetic field induction. So another thing is, if we take not a single loop of electric current, but if we take many loops, like this is one loop, and this is another loop, and then another one, and so many loops, and the electric current will flow here, and such a device is called a solenoid. A solenoid has some length. Well, it looks like a spring wound on some core of magnetic material, and spring wound on some solid body, for example. So it has some length, and it has some number of turns of the wire, some number of turns. It creates a magnetic field, and inside the solenoid the magnetic field is almost uniform, so that the magnetic field lines inside are such that they are uniform, and outside the magnetic field goes in such a way that, as if this was a bar magnet, the outside magnetic field is such that similar to what is created by a bar magnet. So the magnetic field induction inside turns out to be proportional to the strength of the current flowing here, and it's proportional to the number of turns, number of wounds of the wire, N, and inversely proportional to the length of the solenoid. So N divided by L is the number of turns per unit length, just like number of turns per 1 meter if you have a large solenoid, or a number of turns per a centimeter, for example. It's a number of turns per unit length. Well, you may consider it an experimental fact, but in order to make an equality from this dependence, so this experimental fact just shows that the magnetic field strength inside is proportional to the current strength, and directly proportional to the number of turns, and inversely proportional to the length of the solenoid. But if we want to calculate the magnetic field induction inside, then we must introduce some coefficient. some coefficient of proportionality here, and this coefficient is called mu 0, and this coefficient is called magnetic permeability. This coefficient is called a magnetic permeability, and it was derived theoretically to be equal to 4 pi times 10 to the minus 7 power in international system, in SI system. Certainly it has some units of measurement. What should be the units of measurement of this magnetic permeability, mu 0? The units of measurement must be such that in the result of application of this coefficient, we obtain Tesla to measure the magnetic field. So it must contain Tesla, and the electric current is measured in amperes, but amperes must be cancelled here, so the unit of measurement of mu 0 should contain amperes in denominator, and here we have meters in denominator, so there should be some meters in the numerator. That must be a unit of measurement of mu 0 in international system, international SI system. If you apply such a coefficient having these units of measurement into this formula, then amperes will cancel and meters will cancel, and what remains Tesla. That is what we need, just what we need. Such is the unit. Huh? A what?
Unit for the turns, we don't have one.
Unit for what?
Turns, number of turns.
Number of turns is just a number, no units of measurements. It's just the number of turns, like 25, no units. Also, there is such an interesting thing as magnetic materials. If we take some magnetic material, for example, made of iron, and insert it inside the solenoid, then the iron will be magnetized. There will be an induced magnetic moment of this iron core inserted in solenoid, and that will increase the magnetic field. That will increase the magnetic field. So if the solenoid contains some magnetic, some core made of magnetic material, then the magnetic field induction will be larger than given by this formula. And in order to include this phenomena, people have introduced a special coefficient which is called a magnetic permeability of a material, and the formula will be the same, the remaining part of the formula will be the same, number of turns over L. So that will be the magnetic field induction inside a magnetic material. And this coefficient mu is has no dimension, it's just a number showing how many times will the magnetic field be increased by the presence of such magnetic material. So there are many magnetic materials. Actually, any material you find in the world has some magnetic properties, any material. And for different materials, this quantity, magnetic permeability, may have different values. For example, if mu is slightly smaller than a unity, then such material is called diamagnetics. Diamagnetics. If mu is larger than unity, but not very large numbers, just a little bit larger than unity, then such material is called paramagnetic. Paramagnetic material. But if mu is very large, many times larger than unity, maybe hundreds of times larger, then such material is called ferromagnetic. So all the materials which can be found or synthesized have some magnetic properties, and the most important magnetic properties can be categorized according to this definition of diamagnetics and paramagnetics and ferromagnetics. All such materials have different magnetic permeability. The most interesting case, certainly, to create strong magnetic fields is the case of ferromagnetics, because they have mu as a large number, and so they increase the magnetic field by hundreds and even thousands of times. Which materials are ferromagnetics? Like ferrum, like nickel, and different alloys of ferrum and nickel and other metals and other substances. But paramagnetic materials do not influence magnetic field strongly. They just influence a little bit. But paramagnetic materials are very interesting because they resemble interesting properties in quickly varying magnetic fields. If the magnetic field is alternating with some high frequency like megahertz, then such paramagnetic material resembles some paramagnetic resonances, which are very interesting phenomena. Paramagnetic resonances allow one to study the structure of complicated molecules in paramagnetic materials. So any type of magnetic substances has interesting physical properties, actually. So I would like to solve a small problem which has this statement. Consider a solenoid which has the length 20 centimeters, and the current flowing in solenoid is 0.1 ampere. Such an ordinary solenoid, not very large, and the number of turns of wire in and this solenoid is 500. And we have to calculate the magnetic field strength inside such a solenoid created by this current. So it can be directly calculated using this formula. That will be mu zero. You may call it mu naught or mu zero. Anyway, it's also called, sometimes people say mu naught if you have zero. Then it will be an electric current, the number of turns of wire, and the length of the solenoid. So mu naught is 4 pi times 10 to the minus 7 in international system. The electric current is 0.1 ampere, and the number of N is 500 divided by L, 20 centimeters. Centimeter is not a part of international system, so we must convert this unit of measurement into meters in order to calculate everything in the international system. So this will be 0.2 meters, and this number 0.2 will be inserted here in the denominator. And so that will be what? That will be 0.1 divided by 0.2. I will put it this way, 500 divided by 2, nothing more is needed, 4 pi 10 to the minus 7. Let's calculate it. 500 divided by 2 will give you 250. 250 times 4, this one will give you 1000. 1000, 10 to the power of 3. And pi, so we have pi 10 minus 7 plus 3 will be minus 4. And what are the units of measurement? Tesla. So that magnetic field induction. So that will give us pi is 3.14 times minus 4 Tesla. Tesla is not a very convenient unit. I told you that Tesla is a very large magnetic field, so people often use other unit which is called millitesla. Millitesla is 1,000th part of Tesla. So in order to convert it to millitesla, we may use such a simple relationship that 1 Tesla equals 1,000 millitesla. And if we substitute 1,000 millitesla for 1 Tesla here, then we will obtain 10 to the minus first power, and this coefficient 3 times 14 millitesla. That will be a more convenient unit measurement of a magnetic field. So this will be approximately equal to, I will take into account 10 to the minus 1 power, 0.314 millitesla. Why approximately? Because I used an approximate value of pi. Pi is approximately 314. I omit some other digits here. So, such is the calculation of magnetic field inside the solenoid. You must take into account the strength of the current and the number of turns of the wire, and the length of the solenoid, that is the number of turns per unit length, and the magnetic constant μ0. So that is the magnetic field inside the empty solenoid, where we have inserted no magnetic core. If we insert magnetic core, we must use a coefficient magnetic permeability, which may change the magnetic field by hundreds of times. It may be hundreds of times larger, or even up to 1,000 times larger, if you find a very good ferromagnetic core to be inserted here. Then the magnetic field may be increased considerably, and in this particular case, it may be about 1,000 times larger. That is about 0.3 Tesla instead of millitesla, if you use a magnetic field core, a magnetic core inside the solenoid. So, another thing I wanted to consider will be a magnetic interaction of current with magnetic field. We already discussed this issue. If we have an electric current and an external magnetic field, then there will be a force acting on the current, and the force will be perpendicular to the direction of the current and perpendicular to the magnetic field induction vector. So the force will be perpendicular to this wall, and this force is experimentally found to be proportional to the electric current strength and magnetic field, and also it's proportional to the length of the wire. If we take a small piece of wire, then there will be a small force acting on it, and the force will be perpendicular to this wall, a small force. But if I take a larger section of wire, the force will be larger. So the force acting on some piece of wire is proportional to the length of this wire. Also, it was found experimentally that if the angle between the current and the magnetic field differs from 90 degrees, if it's not the right angle, some other alpha, then there will be sine alpha here in this equation. So that this formula will take its maximum value of IBL when alpha is 90 degrees. Then sine alpha will be unity. That will be the maximum value of the magnetic force acting on the current from the magnetic field. But if alpha is smaller and smaller, if alpha tends to 0, then sine of alpha will be 0 and the magnetic field force will tend to 0. For small alpha, if the magnetic field is directed somehow practically along the current, then the force will tend to 0 due to this coefficient. So this may be considered as an experimental fact. And such a magnetic field force acts on a wire with electric current. But the electric current consists of separate electrically charged particles, like electrons. Actually, we consider the direction of current as the motion of some positively charged particles. And the particles move here along the wire with some velocity. Actually, in some metals, the current is conducted by positively charged holes. In other metals, the current is conducted by negatively charged electrons. So if we consider holes, that's okay, that's a real situation. Sometimes that is so. In semiconductors, there are both holes and electrons, both positively and negatively charged particles, and they will move in opposite directions. In any electrolyte, which is like a solution of salt in water, there will be both positively charged ions and negatively charged ions, and they will form the electric current if you apply some voltage to the electrolyte. So there will be both positively and negatively charged particles moving and creating the current. And therefore, well, it's quite reasonable to assume that the direction of the current coincides with the direction of motion of positively charged particles inside the conductor, even if there are no positively charged particles, but only negatively charged particles. It means that negatively charged electrons move in opposite direction. But anyway, for some conductors, for many, many types of conductors, there are positively charged particles inside it. So if we consider just a single positively charged particle, which has a charge plus q, then we must conclude that the force must act on each moving charge, because the force acts on the wire with the electric current, but the current consists of moving charges. Therefore, each moving charged particle must experience a force acting from the external magnetic field. How can we calculate this force, which acts on a single charged particle moving at a given velocity v? So we must recall that the electric current, by definition, is the amount of charge flowing through a cross-section of the wire during some time interval delta t. By definition, electric current is the charge divided by time period, delta q divided by delta t. That is just the definition of current. So the larger the charge flowing through a cross-section of the wire, the larger will be the current. And if the same charge goes through the cross-section in a smaller interval of time, then the larger will be the current. Okay, so if we substitute this definition of electric current here for the electric current, we will obtain that will be induction of magnetic field, and the definition of electric current will be delta Q divided by delta L and multiplied by L. Well, we assume that alpha is 90 degrees, so that sine is unity. Now, if we take delta L equal to L. So this is delta L, and we take it equal to L. It means that we consider some section of a wire carrying electric current, some section of a wire of the length L, and we consider all the charges on this section of the wire, all the charges here. So delta Q is just the electric charge located on the length L. Then, oh, sorry, that is time, certainly. What? I have to, yes, certainly that is, that is time. Well, but I'm talking about the same thing. If we consider delta Q to be the total charge of moving charged particles located on this distance L, here on this section of the wire, then L divided by delta T will be the velocity of these charges, because during time delta T, all the charges on this section will go to another part of the wire. So that this will be, so this is the definition of electric current, certainly. And so this will be what? L divided by delta T will be the velocity of the current. So I obtain the velocity, I obtain the charge, and magnetic field induction. So in this way we come to a formula which relates the force acting on the charge delta Q moving with velocity v in the external magnetic field B. So if we have a single electron, for example, which has a charge E, then the force acting on a single electron will be given by the charge of the electron, its velocity, and the magnetic field induction. And what is the direction of this force? It will be perpendicular to magnetic field induction vector and perpendicular to velocity. So if the force vector, I'm not using the vector notations, but you must understand that all these quantities are vector quantities. The force is a vector, and V is vector, and B is vector, and actually here is a cross product of two vectors. Have you studied cross products? Okay, so you know what is a vector product, a cross product. So actually here is a vector product. And, but the result will be that the force is perpendicular to the velocity. It means that if the electrically charged particle E has some velocity v, and the magnetic field, for example, is directed perpendicularly to this wall, then the force will act perpendicularly to the velocity. Such a force will change the direction of the velocity. The direction will be changed so that here the particle will have a velocity vector of different direction, and the force will also change its direction because it must always remain perpendicular to the velocity. So that such a force will act on a moving particle, always changing the direction of velocity, but not changing the magnitude of velocity. The magnitude will remain the same. If the magnitude of velocity is the same, it means that the kinetic energy of this particle will remain the same. The kinetic energy will not change. And it means that this force does not perform work. The magnetic force acting on an electrically charged particle, if the particle is free, if it moves in the free space, in vacuum, the particle moves in vacuum, and here is a magnetic field perpendicular to this wall, to this board, then this magnetic field force acting on the particle will perform no work, and it will not change the magnitude of the velocity. It will change only the direction of the velocity. So such a force acting on a charged particle from an external magnetic field is called a Lorentz force. This is a Lorentz force. It seems to be written in this way. I'm not sure if there is T inside or not. I'm not sure. Lorentz TZ or simply Z? I'm not sure. Okay. So it's a Lorentz force acting on a charged particle. And due to this force, the particle will have a circular trajectory. Actually, if you have a magnetic field perpendicular to this board, and the particle moving, the charged particle moving at some velocity v, then the magnetic field will cause the particle change its velocity. And if the magnetic field is uniform, then the curvature of this trajectory will be the same everywhere, and the particle will move along a circular trajectory in such a uniform magnetic field perpendicular to the board. If the particle has some mass m, then the force acting on the particle will be a centripetal force, which can be easily calculated so that mass times acceleration of the particle will be equal to what is the acceleration if the particle goes along the circular trajectory, which has radius r. The acceleration will be given by v squared divided by r. This is the formula which we obtained in kinematics. Centripetal acceleration. And this will be a force acting on the particle from the magnetic field, so that will be the Lorentz force. That will be equal to E, the velocity, that is the charge of the particle, like an electron or proton, and the charge of the particle, its velocity, and the magnetic field induction. So the magnetic field, I remind you, is perpendicular to this board. From here we obtain, from this equation we obtain that one velocity will cancel, and we obtain the result that the radius of the circular trajectory will be equal to mv divided by the strength of magnetic field and the charge of the particle. So particles of different masses will have different trajectories. Particles of small masses will go along a small radius circular trajectory, and a particle with heavier mass will go along such a trajectory of larger radius of curvature in the same magnetic field. So if we have ions, for example, ions, which bear the same electric charge, then the radius of curvature of this trajectory will depend on the mass of the ion, and different ions of different masses will have different radii of curvature, and the heavier ions will go along a different trajectory. So this is ion of mass 1, and this is ion of mass 2, and mass 2 is larger than mass 1, and therefore the trajectory is different. And this is the way to separate ions of different masses. This is the physical principle according to which a mass spectrometer operates. A mass spectrometer which can collect ions on some plate here. The ions will bombard the plate and they will be deposited here and here. And then, after we look at this plate, after some time, we will obtain that some ions have been deposited here and they are electrically charged particles, but if they are negatively charged, then some extra electron will be lost here and it will go into the circuit, into the electrical circuit. And if the ion is positively charged, for example, if they are positively charged ions, then the electron will come here and the ions here will become neutral atoms, because positive charge will be neutralized by an electron which comes here from the ground, for example, from the Earth. So this will be just neutral atoms deposited here on this plate, and when we look at this plate we will see some lines corresponding to the atoms of different masses which were contained in this gas, for example, the ionized gas. And this is the principle of work of a mass spectrometer. We can separate atoms of different masses, even if the mass difference is very small, even if these are isotopes of the same chemical element. And this is the way to see how many isotopes are there in a gas. So the mass spectrometer allows one to analyze the molecular structure of the gas based on the Lorentz force acting on a charged particles moving in the magnetic field. So this is just the physical principle. This is not a detailed discussion of the construction of mass spectrometer, but that is just a physical principle. Well, I think I have enough time to consider to solve a problem, and I will consider problem number 5 or 6. The problem says a current I flows through an infinitely long conductor bent to form a right angle. So there is an infinitely long wire, conducting wire, and it's bent here to form the right angle. And this is the wire through which a current I flows. And the problem suggests to indicate this wire as A, B, and C. So points A and B are infinitely distant points. It means that they are so far away that we may approximately consider this to be a straight infinite wire. What is infinite will be clear just in a few seconds. And we consider the magnetic field here at this point, point O, a point of observation. We consider magnetic field created by this current. And the problem says how many times will the intensity of the magnetic field change at this point of observation if an infinitely long straight conductor BD, which is another conductor here, BD, also infinitely long, is attached to point B. This wire, a new wire, is attached here to point B, so that the current I branches at point B. The current I will branch at point B, and some part of current I will flow here, like I1, and that will be I2. And it says that the current I is divided into 2 equal parts, so that the current here will be I divided by 2, and this current will be I divided by 2, into 2 equal parts at point B. After I connect here a new wire, the current which was here will be divided into 2 equal parts. Well, so originally we had the first wire bent at the right angle. And there was a current here, originally current I, and there was the magnetic field in the point of observation B, and that was the original or initial magnetic field, BI. And then we connected another infinitely long wire, straight wire, to the point B in such a way that the current was divided into 2 equal parts at the point B. And the question is, how many times will the magnetic field change? So we need to find the ratio of the initial magnetic field to the final magnetic field. The final, after we attach a new wire here. Now it's just the right time to discuss what is infinite in this problem. What is infinitely long wire? What is infinitely distant point A and infinitely distant point D? It means that the distance AB is much, much larger than this distance BO. Certainly, everybody understands that it's impossible to choose a really infinite wire going to distant stars. Absolutely absurd assumption. The wire is finite and it may be just 1 meter long, but 1 meter is infinite if this distance is about half a centimeter. So the distance BO must be much smaller than the distance BA. And that is what we mean when we say that the wire is infinite long straight wire. When physicists say, when a mathematician says infinite, he means this actually infinite and nothing more. But when physicist tells infinite, he means just certainly not infinite, but that one thing is much larger than another thing. Much, much larger. That is what we mean by saying infinitely large or infinitely small. So, initial magnetic field at the point of observation must certainly be proportional to this strength of electric current. It must be proportional to the strength of electric current. And the coefficient of proportionality, there is some coefficient. I will not even try to derive the exact formula for this coefficient of proportionality. I need just to know that there is some coefficient of proportionality between this current and the magnetic field in point O created by this current. What magnetic field is created by another branch of this current B on the wire BC? As this current goes in this direction, and this direction coincides with point O, then this current I1 creates no magnetic field in this point. None at all. So all the magnetic field created in this point is created by the initial current I. And the current I1 creates no magnetic field here, because this point is just lies on the same line, BC, belongs to the same line BC. So the initial field in the point of observation is created by the initial current. And then we attach here a new wire, a new conducting wire, so that there will be another current here created, creating the magnetic field also in this point. So that the final magnetic field will consist of the initial magnetic field, which is Ki, that is initial, plus the magnetic field created by the second current, which will be also proportional to the current in this piece of wire, with the same coefficient of proportionality, because geometry of this wire is the same as the first wire. The geometry is the same. With respect to this point, this is just an infinite wire ending at this point, and this is also an infinite wire ending at this point. So the geometry is absolutely similar, and therefore the coefficients of proportionality is similar, but this part of magnetic field is created by the first part of the wire, and the second part of magnetic field is created by the second part of this wire, by the section BD. And therefore, that will be Ki 3/2. And so what we need to know in this problem is the initial magnetic field divided by the final, or vice versa, final divided by the initial. And it will be, initial is Ki, and the final will be 3/2 Ki. So the answer will be 2/3. So that the final magnetic field will be 50% larger than the initial magnetic field. Final magnetic field will be 3/2 initial magnetic field. That is 50% larger than the initial magnetic field. So after attaching a new wire here and connecting it to point B, we will obtain magnetic field here which is equal the initial magnetic field in 3.2, coefficient 3.2. And what about the direction of these magnetic fields? Do they have the same direction or opposite direction? That is initial and final. That is initial magnetic field and this additive. Will they have the same direction or opposite direction? They will have certainly the same direction, because this current will create magnetic field, circular magnetic field around it by the right-hand rule. The lines of magnetic field will be directed so, and this current will create the same magnetic field arranged in the same way. So the direction here will be from the board to the classroom, created both by the first current and by the second current. Both directions are the same. Therefore, we can use the plus sign here, because one magnetic field is just adding to another magnetic field. They have similar direction. But should they have opposite directions, then we should use minus sign here. Just understand it. Okay.
If the question tells us the point of observation is from there, or we have just assumed the point of observation?
The question is to find how many times was the magnetic field changed.
Yes, but not point of observation. The zero from all to B.
What is the question? That is the point of observation.
Is the question told us the point of observation from there, or we have just assumed that is the point of observation?
That is the point of observation, and magnetic field is directed here at this point. The magnetic field is directed here. Is it the question? And what is the question?
Like from the question there,
is
it telling us the point of observation is from that point there, from the top there?
Look at this problem. What is the question here? Probably you did not understand the question. That is 4, 5, 4, 6. It's clearly formulated. Maybe I have.
Asking the point O, how do we assume that it's there?
Why do we assume that this is belonging to this line?
Yeah.
It's directly stated in the problem.
Oh, yeah.
Yes, it's the statement in the problem. Yes, probably I have not told you clearly that this point O belongs to the line BC. Yes, this is directly stated in the problem. Absolutely. So I understand that's all the time we have. So this is the end of our lecture. Thank you and goodbye. And next time we will consider some problems, more problems and more physical phenomena related to magnetism. Okay?